Cool. So that's too easy then. You guys need another assignment immediately. But before you get another assignment, you need to work on a bigger data set. That's really the punchline of this project. Did you write the nearest neighbor solution yet? Yes, no, maybe? I asked that in Slack and you can answer if you're participating. All right, so we're doing all right. Yeah, Julian, so you're supposed to have done that. The assignment had two parts. First, you do the permutations component. And I actually gave you that heap algorithm, rather heaps algorithm, that generates all the permutations of items in a set. And so if you use that algorithm that I gave you a few days ago, then you should have the solution to the toy cities problem that I gave you, and we've talked about it in Slack a little bit today. So it's easy to know whether you've got it right. And you're guaranteed to get it right. That's the goal of doing permutation-based search inside of some difficult problem space. And you can do a permutation-based search like this on every problem that exists. But most problems are much bigger than 4 items. All right, so that's the next part of the assignment that I wanted to share with you guys. I coded around with it a bit today, and I want to show you what I got. And the thing that I got is I downloaded this cool file called USA 115475.tsp, and it's a scientific research data set. It's already open in one of my windows. This one, of course. Okay. So, a few of you have already gotten through the algorithmic part of the assignment, and now you get to work on the analysis part of the assignment, which is essentially extra credit that you're getting right now. Those of you who are still working on computing the shortest path for the traveling salesman using all the permutations of the set, this data set will extend that work and make it more interesting fast. Okay, so I got this file, USA 115475, and it's got 7 lines of comments at the top. And then starting on the 8th line here, it's got an unnamed city with an unnamed coordinate pair. Okay, and I don't know what the metric is for these coordinates. They are latitude, longitude coordinates that have been converted into Euclidean space. And I don't know what algorithm they use to convert them into Euclidean space. But it wouldn't be that hard to figure it out. And that's something that we're going to talk about. Before we talk about that, I want to point out something that might not have crossed your mind, that I want to cross your mind, and that is that Euclidean coordinates. Okay, so Euclidean coordinates mean something that's on a Euclidean plane, and a Euclidean plane is really a graph in essence. It's one of those graphs that you've seen before that has an x coordinate and a y coordinate, and the plane is perfectly straight up and down, and you can have numbers at any position. You can in fact have kind of any data stored at a position on that plane, position X, position Y. And the equation that I gave you for calculating the distance between 2 points, 0.1x minus 0.2x squared plus 0.1y minus 0.2y squared, square root of that quantity, is only valid for Euclidean coordinates, which is like, well, and this isn't even literally accurate because this thing has flex to it. But you know, my book, it's a Euclidean plane. It has an x coordinate and a y coordinate. And we could reason about what's on the plane. We could draw pictures on it, which is a big, big part of computer science. It's how your computer screens work, first and foremost. That doesn't actually apply to cities on the surface of the Earth. The surface of the Earth is a sphere, right? And latitude, longitude coordinates, while you can convert them into a decimal value, latitude and longitude coordinates don't actually tell you the distance between two cities, because you have to compute their difference using something called polar geometry. And it's a pain. It's an algorithm that's hard, okay? Because remember that the lines of latitude are equidistantly spaced up the Earth, and the lines of longitude are equidistantly spaced at the equator. But as you move toward the poles, they get closer and closer together. So there's a function that describes how far apart those points really are across the surface. And the Euclidean distance equation that I gave you a minute ago would only, even if you converted the latitude and longitude into decimal values, would measure the distance between them straight through the Earth, not across the surface. Okay, so we don't know what method was used to produce these values. But what we do know is that there are 115,000 cities contained in this file. I just press Shift G and it takes me right to the bottom. There's the last city. Oh yeah, so I was clicking on this because I wanted to show you. Here's a map of those coordinates on this map, whatever this projection is. It's a mapping projection from a sphere, the actual globe, to some mathematical function that converts it into this 2D grid. So this data set can't be solved with the permutation approach. It can't be solved at all right? Before I go on from this to the next little piece of code I wanted to share with you, I also downloaded another file that goes with this. USA 115475 cities. Don't CD into it, Vim into it. And this one, let's see if it matches. It's pretty important that it matches. Okay, 33613.581588, nice. 86118.3061. This first coordinate is Lincoln, Alabama, I think, located in the county of Talladega. And Denver is here on line 2524. No, this is a city called Denver in Tallapoosa, Alabama. There's Denver in Denver County on line 14,336. Okay. So the reason I'm showing this to you is that we've got two disjoint data sets, but there's something called a parallel array. Okay. A parallel array means that you've got one array containing some set of data, and you've got another array containing another set of data, and their indices connect them. Their indices actually allow you to construct a bigger data set from the two arrays, and it's a common technique that's used in not just algorithmic programming, but in computer science in general. Okay, so if there's two arrays that are being used and they're the same length, and they store similar data but not the same data, that's called a parallel array. what's useful about this is that we could, using either one of these files, we could read this into JavaScript, and then we could pick the cities that we wanted, right? We could only pick the cities that are in Denver County, or we could only pick the cities that are in Colorado, or we could just pick exactly the ones that we wanted. We could read this file, we could parse it with JavaScript, and insert the cities into a hash map by name. And then we could say, I want to know the real coordinates in whatever this conversion system is for my 14 favorite towns. And I want to do a traveling salesman problem on them, and it'll be the real thing, and it'll tell you the best sequence of towns to visit within some epsilon that involves like roads that are windy, or towns, well, maybe even towns that aren't connected. There could be towns that don't have a connection. Building this data set involved careful consideration on the part of the people who produced it. And there are clauses and there are exceptions, and they made special rules. And so you can't make an assumption about exactly what it's good for, which we've talked about before. You know, it depends. Almost everything has so many layers of detail that went into that decision that you can't just look at it and be like, well, duh, of course they did it the way that I would assume they did it. Stop thinking that way. You're a computer programmer now. They definitely didn't do it the way that you would try to do it the first time. They definitely didn't make the same assumptions that you did. And that doesn't prevent you from playing with the code, but it prevents you from making any strong claims about what it is. All right, so I made this tsp.js file. I'm just kind of gently refactoring my code. I copied the heaps algorithm into a new file. I wrote a distance function. I put the cities in at the top. And then I wrote a little object called TSP, and it keeps a shortest path and a shortest path length. And I passed it a function called doTSP. Okay, and so this TSP is primarily for a full path, right? It depends upon a complete path. So I wouldn't use this TSP object for my nearest neighbor approach. But it works great for dealing with the full set of permutations. So here inside of heaps algorithm, where I generate all the permutations, if I'm down to n equals 1 in the algorithm, I actually I check to see if there's an x value in the set for the first object. And if there is, I send it into tsp.doTSP, and it calculates the length of the paths, and then it compares them with the current best and saves it if it's better. And if it doesn't have an x, I just output it so that I can continue to play with my little heaps algorithm if I want to. All right, I renamed my base level function all permutations TSP, and then it just calls heaps algorithm using the size of the set that I pass into it. And then at the end of it, I call show me the shortest path length from my TSP and the shortest path. I commented out my game versions that just show me the permutations being generated, and I call it on cities. And I'll just comment out this one because that's where things get interesting. All right, great. Oh, it looks like I'm doing it anyway. Am I looking at the wrong file? I'm surprised that it ran. Oh, no. This is just showing me the first 11. That's the goal. So I ran all permutations TSP. And it says, here's the shortest path. And there's a number of matches to the shortest path because it's such a simple problem that there's, and because the distances are so completely made up, I just typed in values that in my mind's eye had some physical correlation to the real distances and directions in some made up map. So 723.61 is the shortest path between these 4 cities in this funny little data set. And like I said, there's a few different orderings, but if you go from Salt Lake City to Cheyenne to Santa Fe to Denver in this model, which sounds like complete nonsense to me, then that's the shortest path. Yeah. And that's a terrible path. And it's not even true, actually. So I need to look more closely at this. How could the trip from Cheyenne to Santa Fe to Denver be shorter than going from Cheyenne to Denver first? Cheyenne to Santa Fe is 150, and Santa Fe to Denver is 150. Cheyenne to Denver is only 100, and Denver to Santa Fe is 150. So maybe I've got a terrible flaw in my algorithm. Gonna have to double check that.
Hey, Thompson.
Hey, Patrick.
How you doing? I was just curious to see that you had 11 results for the paths that were shortest.
Are you talking about this?
Yeah.
It's unrelated. It's on the next line, which I want to talk about. And it's too bad that I discovered something looking at this algorithm that makes me think, that's nonsense. Like, did I implement my distance function differently? Patrick, I'm pretty sure you got the exact same shortest path length too, right?
Yeah, I had 8 routes that were all 723 whatever long.
Right.
And then comparing to the maximum number, my first 3 results, one was 823, the next 2 were 800, and then it got to where they were just that was how I ended up with the 11 versions. But yeah, I was curious how you were handling that. If you were comparing to, you mentioned something about finding the maximum safe integer in JavaScript.
Yeah.
And comparing against that for the first shortest value. And yeah, I was just
doing
curious.
that here. Number.max value. So when I create this TSP object, or when I call initialize, I set this dot shortest path length to be number.max value, which is the biggest number that JavaScript can hold. And it's not an integer. Everything in JavaScript is a floating point number. I think it's a double. And then I set the path to be, it should say undefined here probably. I'll change that for consistency. Right. And now, really, I'm stumped because just looking at this path, it seems like this is nonsense. Now, maybe it has to do with, yeah. So this is it. Okay, so if we went from Cheyenne to Denver and then to Santa Fe, then we have to go from Santa Fe back to Salt Lake City, and that is a longer distance, probably. So I'm pretty sure the algorithm works. It's just that doing a traveling salesman problem is not intuitively obvious for anybody. It's hard, and it gets crazy hard. Okay, so this is what I wanted to share with you. The point of this little QA is that I'm refactoring this into something that I think is prettier still. But I read this USA 115475.tsp into my program, and I split it on carriage returns, all 115,000 lines. Okay, now I store value. This is pretty C-looking code, right? I store value 7. That's how long the header is. It would be better to call it header length. And this is what code review is for, by the way. When you sit with someone professionally and say, here's what I wrote, and they say, why don't you name that header length? Because that's a better description of what that is than just header. Header length equals 7 and number of cities equals 11. All right, now I slice my USA TSP, just the first 11 cities. I say pick from 0 plus the header length, because I want to skip the header length. And then I want to slice out from there to the number of cities plus the header length, which is just the JavaScript slice function. And now I have to reformat them. They need .x and .y values for my function to work on them. So I say USA cities equals USA cities unformatted .map. And then I split the line by white space. And then I just return name, which is the number. And I return X and Y for that city. So I've reformatted the data that came in here, or even better put, And reformatting like this is a common thing. And I thought about assigning it to you in some special way, and maybe I will. So I took the data from this file and I converted it into this format, except that I don't know what the name is. And I could get the name. Remember, I showed you that to you, and it would be good to get the name. It's in this other file. If you have the integer value, then you just go to the position of this array for that integer value, and you pull this particular string out, and then you know the name of the town that's being indexed. So here's what I did then. I made things more interesting. I did 7. So now I want 7 cities in my set, not 4, because 4 is boring. I'm going from the top, so it's these 7 cities in Alabama: Lincoln, Abanda, Abbeville, Aberfoyle, Abernant, Acton, and Ada. Okay, which is, again, why I showed this to you, because I'm going to share this file with you in the repository. And it would be cool if you made a TSP that actually had cities that we all cared about. Once you get more than 4 cities in your TSP, the likelihood that you're going to get not 11 different matches that all have the same length is pretty low. Cool. So it ran, and it says that the shortest path is 6220.3. What metric is that? I don't know. You could solve it, right? Here's the thing. Here's how we could figure it out. We'd have to say, how far is Lincoln, Alabama from Abanda, Alabama? And then we'll calculate the distance of these two values from one another. And then we'll know. Maybe it's meters. Maybe it's probably not miles, because 6,200 miles is a whole lot. Maybe it's thousandth of a mile. I don't know. Meters seems like as good a guess as any. It would be kind of surprising if all these cities were within 6 kilometers of one another. But we could come up with a conversion factor for it to be completely real and not just a toy. All right, so then what order do you visit them in? 7 to 2 to 3 to 4 to 5 to 6, then back to 1. So maybe they are super close to one another, since you visit them in order. What happens if we run it again? The same optimum. But it should be that way anyway, because the algorithm that we're using, Heap's algorithm, is completely deterministic. So the last one with the shortest length is going to get evaluated each time. Let's keep going. Let's do 8 cities. That computed fast. And here's the ordering to have the shortest path between these 8 cities. And it's only a little bit farther. It's 122 zoltas farther. And I continued pushing this up to see how far I could get with my permutations. You see what's happening now? I want to visit 10 whole cities. But I can't. It takes too long. Oh, that wasn't too bad. 8,600 zoltas to visit city 8, then 9, then 2, 3, 4, 5, 6, 7, then back to 10, then to 1, then back to 8. And then the last thing I wanted to show you from this, so I'm going to put these files in the repository, and I want you to figure out the biggest size of cities that your Heaps algorithm version of the TSP can solve. And that's a function of how long you're willing to wait. Don't wait more than 5 minutes. You should assume that the length of the calculation will go up by the size of the set each time you add a value, right? So this size 10, oh yeah, and this is crucial. I quit out of that. Now you just do this. This is one of the reasons you use the command line from Linux, but there are many more. Time node tsp.js. And now it's keeping a timer. It runs a program before it runs node that records the current time, and then it waits for node to exit. And when node exits with the function that we called for it, it says how long it took to run. 14.7 seconds. Primo. Time is primo. Okay, so 14.7 seconds. It actually only took 14.2 seconds. Some of those seconds were the operating system. 1/4 of a second was the operating system doing its own thing. And then apparently there's another 1/4 of a second that just disappeared into the void there, like idle time, waiting for the operating system to switch. So user time is how long your program really took to run. Each time we bump this number up, numbers of cities, the amount of time goes up by the number that you just raised it to. Okay, so number of cities of size 11 should take approximately 11 times as long as number of cities of 10. And I actually did this, and it took considerably less. It only took like 5 times as long. So why is that? Overhead. That the time that it takes to generate all the permutations is, I don't know, I have to think about that. The point is that with my machine, it terminated in about a minute with 11 cities. But if I bump it up to 12 cities, it's going to take 12 times as long, or 12 minutes. And if I bump it up to 13 cities, it's going to take 13 times as long as 12 minutes, and so on. That's why you need nearest neighbor. All right. So finish your permutation addition and see how many cities you can do with it. Here's where things get interesting, because after you've got your permutations algorithm working, you go straight to your nearest neighbor algorithm. And you see how many cities you can compute with that. And you can probably add 100 cities at a time to it, because you're not computing n factorial. You're not using an n factorial algorithm. You're using an algorithm. Let's think about the nearest neighbor algorithm. So if you do it deterministically, that is, you visit each city and then you calculate nearest neighbor from that city, think about what it looks like. Let's go back to the O of n graph picture that I showed you. I'll just have to go to Lucidchart. Lambda school, algorithm complexity. Yeah, so what are we looking at? N factorial, I can't even draw a picture of it. It gets really big really fast. However, if we have n cities and we visit each city one time, and then from that city, we visit the remainder of the cities, what's the complexity of that? So from that city, what we're going to do is we're going to visit n-1 cities. So that city visits n-1 cities. So what's the complexity there? It's 1 plus n. And then from that city, it's going to visit n-2 cities. And from that city, it's going to visit n-3 cities. And so the full complexity of this visitation is log n. I need to draw a picture of that. So from each vertex, we visit log n cities down this branch, and then we go to the next city and we visit log n cities. And then we go to the next city and we visit log n cities from that. So it's n across the top, log n. As trees, it has this shape, almost. So by changing from an O of n factorial algorithm to an O of n log n algorithm, you're going to find that you can compute way more cities in your path. And what's really interesting for you to do, look, it only took, okay, so 3 minutes and 1 second. What is that? What did we do before? 14? 15 times 11 is 165. Isn't that what I did? Yeah. So it was a little bit less than 11 times as much. 254, what's that? That's 10 seconds longer than the expected increase in time to run it on a city of size 11. So as you can see, you just can't run it on a large group. But using the nearest neighbor algorithm, the amount of time that it takes to run is only going to go up by essentially 1 times log of your data set for each new city that you add. So if it took 14 seconds to run on 10 cities and we added 1 city, it would take 15 seconds to run, or 16 seconds, or maybe 18 seconds. It would add 1 second for the size of n growing, and then it would add log n seconds for exploring the tree. Okay, so these two data sets and the code that I've generated here for doing permutations, which I want you to build your own, are going to go into the repository, and you can pull it down and start playing with the larger data sets. And you're going to compare the execution time for the nearest neighbor algorithm versus the all permutations algorithm. Any questions? If you have a faster computer than me, then your computer will take less time on 11 cities. And if you have a slower computer than me, then your time divided by my time is, well, my time divided by your time is how much slower than my computer your computer is. This is a long get diff. $230,000 lines because of these huge files that are attached to it. It's a megabyte. No, it's 10 megabytes. Great. All right. I don't see any questions, so I'll see you all tomorrow.